Okay, welcome back. Today we're discussing the multi-degree of freedom systems, and we're going to use Newton's laws and introduce the concept of Lagrange equation in deriving the equation of motion for a multi-degree of freedom system. As we've been discussing in the last couple of sessions, we have introduced the concept of equation of motion. And we have predominantly focused on single degree of freedom systems. And in single degree of freedom systems, we have had this inertial term, the damping term, and the stiffness term. And the parameters that we've been dealing with have been the one-dimensional. So we've been dealing with constants. When it comes to the mass matrix or the damping matrix or the stiffness matrix. So these have been constants, and our acceleration, velocity, and displacement terms have been one-dimensional as well. And the kind of structure that we've been dealing with mostly has been this lollipop structure with the mass on the top and the stiffness and damping parameters. And we've only had one degree of freedom, and this degree of freedom has been called the U. Okay, now what we want to focus on is multi-degree of freedom systems. As we mentioned, the mass is now a matrix, so we have U dot dot. U is now a vector. So again, we have C U plus K U. And this all is equal to a vector of forces. So we have matrices now. For damping, mass, and stiffness matrices, the stiffness terms, and we have got vectors when it comes to our accelerations, velocities, and displacements, and forces. Okay, and an example of a multi-degree of freedom system, for instance, is one that looks like this. We could have a sort of a multi-story lollipop structure where we can have 3 degrees of freedom. So here's an example. We can have x1, x2, and x3. And for each of these elements, we have a mass element, mass term, stiffness and damping terms, and we can also have forces applied to each of the degrees of freedom. And so let's do an example now, and by doing this example I can introduce the concept of Newton's laws for multi-degree of freedom systems. And so to do that, I want to introduce this 3-story building. So we're doing an example here. And this 3-story building has, again, mass parameters M1, M2, and M3. It has the degrees of freedom X1, X2, and X3. And it has these external forces that are being applied. We've got P3, P2, and lastly P1, and we also have the stiffness and damping parameters, which are K1, C1, K2, C2, K3, C3. Here it is. And the kind of framing that we're dealing with in a structure like this would be columns that are flexible and beams that are infinitely rigid. And this makes it easier for us to do analysis because then we only have to look at the lateral degrees of freedom. We don't have to look at some of the rotational and vertical components. Okay, so what I want to do now is to derive my stiffness matrix. So let's write it down. I want to do the stiffness matrix. And this is very much similar to what we have discussed in structural analysis, where anytime we're analyzing a degree of freedom, we let that degree of freedom be displaced by a unity, and we let all other degrees of freedom equal to 0. So that's something I want to do now. So what I'm going to do is to draw my 3-story building as a lollipop model, kind of like that. And what I want to do is to let u1 equal to 1. So in that case, I'm going to have a deformation that looks somewhat like this. And in this case, u2 is equal to 0, and u3 is equal to 0. Okay, so now that I'm looking for stiffness components, I'm only going to be focused on the stiffness parameters. So if I have, if I want to find out the resultant force as a byproduct of this unity displacement, I'm going to put an F1 here, and F1 is really standing for that resultant force. And I'm going to have an F2 here that is sort of countering that, and the force on the ground doesn't really matter. So the forces that I expect this column to experience in the bottom story is going to be K1. So we have a unity displacement times K1, and that's the force we're expecting in the bottom column. In the second floor column, I expect a K2 as well. Okay, so now what I want to do now is to create my stiffness matrix and to really plug in the parameters as I go along. So I've got my capital K, which is my stiffness matrix, and what I'm doing now is to plug in all these parameters. I have 3 degrees of freedom. My stiffness matrix will be a 3 by 3 matrix. So I will have, for the first term, K1 plus K2. So that's the force that is required to have this unity motion, and it equals K1 plus K2. Now, for the second term, I'm going to have minus K2, because this K2 and F2 are in the same direction, so when we add them together and move things across the equal sign, I get a minus K2. And the top column is not really playing a role in this mechanism that is shown here. Alright, I'm going to do one more. We're going to start off with the u2 equaling to 1. So I'm again going to draw my lollipop model. There it is. And this time u2 is equal to 1, and all the other u's are equal to 0. So what I'll have is a displacement that looks somewhat like that. And this time I'm going to have K2, and I'm going to have K3. And so the forces that I'm getting at the locations of the degrees of freedom are as follows. I've got my F1, I've got my F2, and I've got my F3. Okay, so let's go in this matrix and focus on these forces. When I look at F1, the direction of F1 is actually in the same direction as the force K2. So actually I should have drawn F1 in this direction. There we go. And F3 in this direction, because F3 and F1 are countering F2. So F1 and K2 are in the same direction. F1 plus K2 equal to 0. F1 is equal to minus K2. Minus K2. And then for F2, I have K2 plus K3. So that's what I'll write here. And F3 is equal to minus K3. And I can wrap this up by doing the same thing for the very top column of this structure. And what I'll have is 0 minus K3. Maybe I should write that a little nicer. K3, and I've got a K3. Okay, and that's what we have. And again, if you want to think about it in terms of statics, I have my x1, x2, and x3. And these are the states of my system. Alright, so I could do the same thing for stiffness. It's not really going to matter. Stiffness and damping are alright, I should have said I could do the same thing for damping. Stiffness and damping have the same relative concept. They are activated in relative terms. So these x's that I've drawn, these degrees of freedom that I have, are my relative degrees of freedom. And so when I'm expressing this column vector in terms of my relative degrees of freedom, I can treat stiffness and damping the same way. So I can have C1 plus C2, I have minus C2, 0, minus C2, C2 plus C3. It's precisely the same matrix structure as the stiffness matrix. So I have a minus C3, 0, minus C3, and C3. Okay, that's what we have. Now, the acquisition of the mass matrix is slightly easier. We don't need to do all those addition and subtractions that result from the relative terms. What I can do when I'm developing my mass matrix is to simply look at my structural system, draw the lollipop model, and accelerate each of them separately. So I can accelerate the first one with u1 dot dot, and what I'll get is a force for the first element. So since this is m1, I'll have an m1 here, and everything else is equal to 0. They don't really play a part. Again, with m2 I'll have the same, but with m3 I'll have the same thing as well. m2 and m3, and there's a 0 here and a 0 here. Okay, and lastly, I can create a vector of all my forces. So I'll have P1T and P3T. This is really what we have. And putting all these together, I'll have my mass matrix. I'll have x1, x2, x3 dot dot. Oops, maybe I can draw these nicer. It's a little difficult drawing lines with the toplet that I have, but here it is. And again, this vector manifests itself in terms of velocity 1. So I'll have x3. And lastly, I have my stiffness matrix, and that goes with the displacements or the deformations. So x1, x2, and x3. There we go. And that equals to P1T, P2T, and P3T. Okay, we've completed our equation of motion for the multi-degree of freedom system, and we've noticed that for a 3-degree of freedom system, my mass, damping, and stiffness matrices will be 3x3 matrices. So anytime I have n degrees of freedom, I expect that my mass and stiffness and damping matrices will be n by n. Okay, so now I want to take a sidestep and discuss about a new topic, which is the Lagrange equation concept, and really explain why it's useful and how it can help us. Suppose we have a new example. Oops. Suppose we've got this new example. And in this example, we're dealing with a pendulum. Pendulums tend to be quite nonlinear because now we're dealing with rotations. So we've got this hook hanging from the ceiling, and let's draw a straight line. There it is. And I want to draw a pendulum that is hung from this hook, kind of like that. And let's see if I can draw my circle here. And this is the mass for my pendulum. And this mass has an amplitude of m. This arm, the pendulum arm, has a length L. We've got the coordinate systems x and y, and we've got the gravitational pull going down with a magnitude of g, and we've got this degree of freedom, which we're going to call theta. So this time our degree of freedom is rotational, and it's a little different when you handle things in the rotational sense, because now you have to deal with sines and cosines, and those are nonlinear functions. In fact, if I were to tell you what the equation of motion for a system like this would be, it is theta dot dot plus g over L sine theta is equal to 0. Okay, so this is clearly a nonlinear equation of motion, and it's the equation of motion for a simple pendulum, and it's really quite hard to obtain such equations of motion using Newton's laws. It's doable, it's definitely doable, but it's difficult. And for this reason, we have to introduce the concept of a Lagrange equation, which I'm going to write here. So we're going to introduce Lagrange equation. And with this equation, you can pretty much describe any equation of motion for any mechanical system. And it's very easy. The equation looks actually sophisticated, but as we go through the terms, it's going to sound and look very easy. So I'm going to write the equation down here, and then we're going to work with it in obtaining this simple pendulum equation of motion. So I have it d over dt partial t, and then there's a minus here, got another partial term here, and this is where really what the Lagrange equation looks like, and it typically equals some sort of force function at the very end. So what are these t's and v's and q's? So this is an equation that deals with energy. So we have T, which is our kinetic energy. And with kinetic energy, the easiest way to think about it is any object that has a velocity has kinetic energy. That's really what kinetic energy means. And V is potential energy. So the equation for the kinetic energy, if we remember correctly, is 1/2 mass times velocity square. If I'm thinking about the velocity of this mass, I can simply write, and my degree of freedom, by the way, is theta, I can simply write 1/2 m L theta. And this is squared, because L theta dot is equal to V dot. And I can take the square terms and express my potential or kinetic energy equation as, and that's what I'll have. Now, when I want to do my potential energy has to do with the mass having some sort of elevation, and the potential component comes from the gravitational pull of the Earth. So as we elevate this mass, we're increasing its potential energy. Another way of thinking about potential energy is the energy that exists in the static motion, or in the static condition. So we can also have springs that are loaded, and the contracting action of a spring can give us potential energy. Or we could have the following condition where elevating a mass can increase its potential energy. So what I can have is V is equal to mgh. H is the height of this mass. I'm gonna start recording H from this bottom position where the mass originally must have been. So I'm gonna measure it this way. So what I'll have is mgl minus L cosine theta. And what I want to do is to pull this L out, and I'll get mgl1 minus cosine theta. And the only degree of freedom that I have here is this theta, and so that's what the QIs are. So the only QI that I have is theta. I know this lecture is focused on multi-degree of freedom systems, but it's very critical that I show you how Lagrange equations work with a single degree of freedom system, and at the very end of this lecture I will introduce a double pendulum system and also provide you with the kinetic and potential energy equations and let you do all the derivations. So let's continue on with this simple pendulum and see how things end up. So I'm going to start off with my Lagrange equation, which was d over dt partial t partial qi dot minus this term plus this term. And this whole thing equals force, typically. In this example, we don't have a force, so let this equal to 0. And what I want to do now is to focus on this middle term. So I have partial t over partial q, and in this case q is equal to theta, so I have partial t partial theta. And if I look at my potential energy equation, let's look at it. I don't have any thetas in this, so if I'm gonna take a derivative with regards to theta, I'm gonna get a value of 0. This is equal to 0. Okay, so what I want to do now is to now focus on the first term. And with the first thing, we have d over dt and this partial term. Okay, so we've got d over dt, and we're taking partial derivatives with regards to theta, and so we're doing one half ml squared theta squared. This is what we had. When I take the derivative with regards to theta dot, what I'll end up with is d over dt, and I'll have ml squared theta. And if I take the derivative with regards to time now, I'll have ml squared theta dot dot. And lastly, I want to work with this potential energy term, and what I'll get is the following. And this time we have mgl sine theta. Alright, let's put it all together now, and we get the following structure for the equation of motion. We have ml squared theta dot dot plus mgl sine theta, and this equals to 0. And this is my nonlinear equation of motion. What I can also do is to linearize this. I can linearize this by letting, first of all, simplifying it. So when I simplify it, I'll have the following structure, and then I want to linearize. The first term is already linear, so this is what I'll have. And now I want to linearize the second term. When theta is really small, theta is almost 0, or actually quite small, sine theta is equal to theta. And that's how we can linearize this equation of motion. So this is equal to 0, and we call this the linear EOM. So let's do an example now. Suppose we have our structural system, this pendulum, and this time L is equal to 4 meters and G is equal to 9.81 meter per second squared. What I want to do is to introduce different kind of initial conditions. So what I want to have is to have my pendulum hung from different angles. First of all, the pi/2 angle, and then let it drop and see what happens when I have an initial condition like this. In this case, because I don't have damping, I'm not going to have any reduction in the amplitude. So I suppose if I'm dropping my mass from this position, it will just go down, up and down, and so forth. Let's try it differently. Let's try it here. There we go. It'll probably look somewhat like this. And what I want to show you is whether my linear equation of motion and nonlinear equation of motion match. And if they match, what kind of initial conditions do they match for? So let me pull up my MATLAB script now. And here it is. This is my MATLAB script. I am initializing my parameters. The first initial angle is for my rotation, and the second initial angle is for my second state, which is excuse me, which is acceleration, or excuse me, it is for the velocity. And I have developed my linearized version of the equation of motion here, and I've also developed my nonlinear version here. What I'm doing here is pretty much compiling the nonlinear equation, and then compiling the linear equation, and then lastly plotting the values and converting the values to degrees. Degrees are a little more intuitive to comprehend. To begin with, I want to start off with a really small angle, so perhaps pi/200. So that's my initial angle. And when I compile this, I can see that the two plots are overlapping, and perhaps I should draw a legend, and I can say nonlinear and linear. This makes things a little easier to see. Okay, both linear and nonlinear overlap, so I have very good approximation. Now I want to slowly increase my angle for the initial condition. Okay, so we went up from 2 degrees to 8 degrees, and I'm still getting fairly good approximation between the nonlinear and the linear. The last thing I want to do is to go from a much bigger angle, so maybe pi/5. Let's try that. Alright, here we go. Now we're starting to notice that these two solutions are getting increasingly further apart, and that's because the linear approximation is not very good for larger angles. And this is why we need to incorporate the concept of the Lagrange equation, because the Lagrange equation helps us to identify nonlinear equations of motion, and nonlinear behavior is actually quite different from linear behavior. And that was really the selling point I wanted to get across to you guys. Now what I want to do now is to do a double pendulum and identify what the energy equations are. So let's do an example of that. This time we're doing a double pendulum. And with a double pendulum, I'll have two arms. This is the first arm, and then I can have a second arm, kind of like that. And I'll have a first mass here in this position. It's my first mass, and then I'll have my second mass. Then I've got this hinge or hook up here tied to the roof or the ceiling, and I've got the length L, another length L. I'm assuming these two are the same masses, and I have theta 1 and I've got theta 2. Okay, so now what I want to do is to derive my potential energy equation. So I want to do my let's do the V. First I'm going to focus on the first mass, and with potential energy equation I'm going to measure energy from this bottom position down here. So I have M G L. For the first term I have 2 minus cosine theta 1. Then I have a plus, so energy is added. And then I have MGL, and for the second term I have 1 minus cosine theta 1 plus 1 minus cosine theta 2, and that's what I'll have. For the kinetic energy, I am dealing with velocities. So if I'm thinking in terms of the x and y coordinates, I'll have m over 2 x1 dot squared plus y1 dot squared plus, again we're adding energies, m over 2. The second mass will have the same, will have the velocity of the first mass plus its own velocity. So we can have an energy that looks like this. We have x1 plus x2. There's a square here, plus y1 plus y2, and square that. There it is. That's what we have. And what I can now do is to make sure that all these x1s and y1s and x2s and y2s are expressed in terms of theta 1s and theta 2s. So I have x1 is equal to sine theta 1. So if I'm taking derivatives with regards to time, I have theta 1 cosine theta 1. I can say y1 is equal to 1 minus cosine theta 1, and then I can say the derivative of y1 with regards to time is theta 1 sine theta 1. And pretty much I could do the same for the other terms. For x2 it's equal to sine theta 2, and x2 derivative is the following. and same thing with y2. Okay, and those are the energy equations for the double pendulum structure, which is a multi-degree of freedom system. And clearly the Lagrange equation is the best way to handle such situations. So I hope this lecture helped and you found it useful. If you have any questions, concerns, any comments, leave them in the comment section, and hopefully I can read them and get back to you as soon as I can. And if you have any feedbacks, I'll definitely read them and try to incorporate any kind of comments you have in my future lectures, and to pretty much improve my teaching abilities as well. All right, I'll see you next time. Thank you.